Friends, welcome back to Engineering Mathematics 2. So far we have discussed about the concept of a differential equation, right? And how we are going to recognize an ordinary differential equation, order and degree of a differential equation, and how we are going to write down the general solution of the given differential equation, and what are the characteristics of the solution, and what do you mean by superposition principle, right? And solution to homogeneous linear second order differential equation using auxiliary equation, right? And while writing the general solution, suppose if you get roots real and equal, how we are going to write down? Suppose if you get two distinct roots, how we are going to write down the general solution of the second order differential equation, right? Suppose in case of complex roots, how we are going to write down the general solution of the given differential equation. And along with that, we have also discussed about graphical representation of superposition principle for homogeneous equation, right? And after solving a second order differential equation, how we are going to use a second order differential equation in mechanical engineering field. Especially I have discussed about spring mass system, right? And today I am going to discuss about similar type of problems in electrical science field, right? And we have also discussed about Newton's second law of motion and examples on free damped motion. It means I have given some information regarding what you mean by a damped motion, right? And I have also given the physical interpretation of initial value problem, right? So how do we interpret an initial value problem, and how do we find out the period and frequency of the initial value problem, right? So friends, so far we have discussed all these things, right? So today I have planned to give an information regarding damped motion, right? So friends, I think so far we have observed our differential equations containing only two terms, right? Suppose if I am going to introduce one more term, namely I think I have not included the term dy by dx, right, with some constant, say beta, right? So today my differential equation may contain the term beta into dy by dx, right? So here beta is representing a damped factor, and it is a very important factor, right, in case of spring mass system. Is it clear, right? So we are going to discuss about what is the relationship between beta and k, right? So our differential equation already containing k, a spring constant k, right? So now I am going to discuss about the relationship between beta and k, right? So along with that, we are also discussing about over damped. Sometimes we call it as an over damped. So what do you mean by over damped, right? Sometimes we call it as an critically damped. So what do you mean by critically damped, right? Or critically damped motion. Is it clear? Sometimes we may call it as an under damped motion. Is it clear, right? So we are going to find out the relationship between beta and k, right? Along with that, we are going to define over damped, critically damped and under damped. Simply I can say that 3 D's, right? Over damped, critically damped and under damped. I am going to explain the meaning of these 3 damped motions, right? So we are going to solve examples mathematically, right? I am going to give the graphical representation of over damped, critically damped and under damped motions. Is it clear, right? Along with these things, we are also going to discuss about the role of second order differential equation in electrical sciences, right? So we are already familiar with Kirchhoffs Second Law, right? We have studied in PUC, right? So what is the meaning of Kirchhoffs law, right? How we are going to write down a mathematical term then how we are going to add the terms. Is it clear? Right. So finally we will get a second order differential equation, right? And what is the physical meaning of that second order differential equation, and how we are going to find out the solution. Is it clear? Along with that, just now I have mentioned over damped, critically damped motion and under damped in case of a spring mass system, right? The same thing can be defined in case of electrical sciences also. Is it clear? Right. So by considering one or two examples, I wanted to give the meaning of over damped, critically damped, under damped in electrical science. Is it clear? All right. So after these things, now I am planning to discuss a non-homogeneous second order linear differential equation with constant coefficients. Friends, so far we have discussed only a homogeneous equations, right? So now I am planning to solve some non-homogeneous equations, right? I have already given when we call it as an non-homogeneous equations. When the right hand side member is not equal to 0, then we call it as an non-homogeneous equations, right? So we are going to solve non-homogeneous equations, right? Along with that, I am planning to solve non-homogeneous rules for finding a particular integral in case of certain cases. Is it clear? Non-homogeneous means the right hand side member is not equal to 0, right? So right hand side is not equal to 0 means it may be a function of x, right? It may be a function of x means, so sometimes it may be of the type of exponential function, right? Suppose if it is of the type e to the power ax, right? Then how do we find out a particular integral? Because we know that if the given equation is an non-homogeneous equation, right? I have already explained what is the complete solution of non-homogeneous equation is y is equal to complementary function plus particular integral, right? If the right hand side member is not equal to 0 means I have to calculate particular integral, right? Suppose if I want to calculate particular integral, then I have to observe, right, what is the type of a right hand side member f of x. Is it clear? Suppose if it is e to the power ax, how we are going to find out the particular integral, right? And sometimes it may be of the type x raised to m, where m is an positive integer, right? In that case, how do we calculate a particular solution, right? Not necessarily x to the power m. Sometimes it may be of the type sin ax, or more generally sin of ax plus b, right? Or cos of ax plus b. Is it clear? So in that case, how we are going to find out the particular integral? Is it clear? Right? Along with these forms, a right hand side member may be of the type x into v, right? Again, where v may be a function of x. So in that case, how we are going to find out the particular integral? Is it clear? Right? And lastly, right hand side member f of x is of the type e raised to x into v, right? E raised to x into v, again v may be a function of x. Is it clear? So in that case, how we are going to find out the particular integral? Is it clear? Right? So first we want to define rules for these cases. Then according to the rules, we want to find out the particular integral in all these cases. I am trying to solve at least one example about all these cases, right? So it means we want to develop a method, then we can use the method to solve the equations. Is it clear? Right? Now according to our plan, as I have mentioned, so I am going to introduce one more term in the differential equation, right? Friends, the given differential equation may be in this form: d square x upon dt square plus beta by m into dx by dt plus k by m x is equal to 0. Or the same equation can also be written down m into d square x upon dt square plus beta into dx by dt plus k into x is equal to 0. Then throughout divided by m, right? So what you will get? You will get this equation. Is it clear? Right? Just now I told that we are going to introduce this term, right? So for the purpose of simplification, I want to rewrite this equation in this form, right? So d square x upon dt square plus 2 lambda into dx by dt plus omega square x is equal to 0, right. So, you may ask 2 lambda means what, where 2 lambda is equal to beta by m, right. I have called beta by m as a 2 lambda. Omega square means k by m. Is it clear? Just now I have mentioned we want to find out the relationship between beta and k. Is it clear? Or we can say that relationship between 2 lambda and omega square, right. So, given equation can be written down in this form. I hope now we are able to find out the auxiliary equation of this equation, or before that we can write down in a symbolic form. We can replace d by dt by capital D. Is it clear? I hope you will get capital D square x plus 2 lambda d into x plus omega square x is equal to 0. Is it clear? If I replace capital D by m, I will get an auxiliary equation. Say for example, m square plus 2 lambda m plus omega square is equal to 0. And the corresponding roots are with the usual method, right. I have already explained. If it is an quadratic equation, right. So, now you want to know the formula. Using the formula, we want to find out the value of m. Is it clear? Or it is of the type ax square plus bx plus c is equal to 0. You know the value of a and b, c. Then you want to substitute the values of a, b, c in the standard formula and simplify. I hope we can obtain m1 is equal to minus times of lambda plus square root of lambda square minus omega square. m2 is equal to minus times of lambda minus square root of lambda square minus omega square. Is it clear? Right. So, once we are able to find out the roots, so I hope we know that we want to write down the solution of the given equation, because given equation is an homogeneous equation. Right hand side term is 0. Is it clear? As usual, you can write down the complementary function or general solution. Y is equal to c1 into e to the power m1x, c2 into e to the power m2x. Is it clear? Right. So, before writing the solution, I wanted to give some more information regarding m1 and m2. Is it clear? Right. So, here we have calculated m1 and m2 in the usual way. Is it clear? So, what is the meaning of these things we want to verify? Right. So, we can now distinguish 3 possible cases depending on the algebraic sign of lambda square minus omega square. So, what is the sign of lambda square minus omega square? Because it may be an equal to 0, because we do not know the value of lambda, we do not know the value of omega or omega square or lambda square, right. May be equal to 0, may not be equal to 0. So, may not be equal to 0 means may be greater than 0 or may be less than 0. We want to identify if it is equal to 0, what happened? If it is greater than 0, what happened? If it is less than 0, what happened? Is it clear? That is why I have mentioned 3 possibilities or 3 possible cases. Is it clear? Right. So, since each of the solution contains the damping factor, friends, you want to think about e to the power minus times of lambda into t is the damping factor. Is it clear? Right. So, where lambda is greater than 0, right. The displacement of the mass, right, the displacement of the mass becomes negligible. Is it clear? Right. Over a long period of time. It means as t increases, displacement becomes or tends to 0, and that depends upon this factor. Is it clear? Damping factor, namely e to the power minus lambda into t, right. So, lambda is greater than 0. So, this depends upon the value of lambda square minus omega square. Is it clear? So, it means, so we can take it as an case by case. Suppose if it is greater than 0, what happen? Equal to 0, less than 0. So, we shall discuss one by one, right. Now, I have considered case 1 and I have called it as an over damped motion, right. So, when we call it as an over damped motion, if the value of lambda square minus omega square is greater than 0. Is it clear? Right. So, in this situation, the system is said to be over damped. right, because the damping factor, right, or the damping coefficient beta is large when compared to the spring constant K. Is it clear? It means, so when we get greater than 0, that depends upon beta and K. So what we considered, consider an equation, right? Our differential equation containing beta is some constant, K is some constant. Is it clear? Now that's why we call it as an given differential equation is an equation with constant coefficients, right? So that depends upon the value of beta and K. Suppose if beta is greater than K, then you will get greater than 0. Is it clear? Right? So in such a situation, we call it as an overdamped motion. Is it clear? Right? I hope you will get 2 roots. Is it clear? Right? Now, as usual, you can find out the roots. You can write down the complementary function. Right? We have already calculated the value of m1 and m2, or as usual, you can write down c1 into e to the power m1 into t plus c2 into e to the power m2 into t. Is it clear? And you know the value of m1 and m2, so we can substitute e to the power lambda into t, c1 e to the power square root of lambda square minus omega square into t plus c2 e to the power square root of lambda square minus omega square into t. Right? So this equation represents a smooth and non-oscillatory motion. Is it clear? Right? Here you will get a smooth curve but a non-oscillatory motion because of this factor, namely e to the power lambda into t. That should be noted down. Right? So graphically, how we are going to represent an overdamped motion? Is it clear? Right? So you may get envelopes like this. Is it clear? Either from the above the equilibrium position or from the below the equilibrium position. So for example, if I take this axis as the equilibrium position, is it clear? Right? So you may get curve from above the equilibrium position or from the below the equilibrium position. So for example, in the last session I have shown the spring. Spring is vibrating in the downward direction or upward direction. Say for example, it is moving from downward direction. It may move and it may stop at the equilibrium position. When we draw the curve, I hope you may get a curve like this, or from the above, right? So when we draw the curve, I hope you may get curve like this, like a red color. Is it clear? And we call it as an overdamping, right? Okay. Now I have planned to solve one such type of example, right? So solve the initial value problem, d square x upon dt square plus 5 dx by dt plus 4x is equal to 0, and they have given an initial condition x of 0 is equal to 1, x single prime of 0 is also equal to 1. Right. So friends, it is an as good as earlier example. I think now we are observing a new term, namely 5 times of dx by dt. As usual, you can write down in symbolic form. You can replace d by dt by capital D. Is it clear? D square x plus 5 times of d into x plus 4x is equal to 0. Is it clear? Right. So replace capital D by m. You will get an auxiliary equation. Right. So m square plus 5m, right, plus 4 is equal to 0. It is an homogeneous equation. Right. So from the auxiliary equation, I hope we can obtain 2 factors, namely m plus 1 and into m plus 4. The same terms can be written in terms of factors. So you will get 2 factors. Either first factor may be equal to 0 or second factor may be equal to 0. Suppose first factor is equal to 0, then that from that factor you can write down m plus 1 is equal to 0. That implies m is equal to minus 1 or m1 is equal to minus 1. Is it clear? Similarly, m plus 4 is equal to 0. That implies m2 is equal to or m is equal to minus 4. It means we can obtain 2 roots. Right? So because the given equation is an second order differential equation, I hope we will get 2 roots, namely minus 1 and minus 2. Is it clear? Right? So they have given an initial condition x of 0 is equal to 1. So we can use the initial condition. Is it clear? So before that, you can write down the complementary function. or solution C1 e to the power minus 1 into t plus C2 e to the power minus 4 into t. Is it clear? Right? I said that it is an complementary function, or you may call it as a general solution, because the right hand side member is 0. No question of calculating a particular integral. Is it clear? That's why this becomes an general solution. Right? So by using the given conditions, now I want to calculate the arbitrary constants, namely C1 and C2. Replace t by 0, x of t is equal to 1. Is it clear? I hope we can obtain this equation. 1 is equal to C1 plus C2. Is it clear? When you replace t by 0, I hope you will get 1. Right? So you can obtain C1 plus C2 is equal to 1. Similarly, they have given one more condition, x single prime of 0 is equal to 1. Now I want to use this condition. Is it clear? So using I want to differentiate before substituting the values of the given condition. I want to find out the derivative of this equation. Is it clear? You can differentiate x single prime of t is equal to C1 is constant. It is as good as the derivative of e raised to ax. How we are going to find out the derivative of e raised to x? Exactly in the similar way. Now I want to differentiate e to the power minus 1 into t, means I hope you will get minus times of C1 e to the power minus 1 into t. And similarly, derivative of second term is minus 4 C2 e to the power minus 4t. Right? So now we can substitute the values. We can obtain one more equation, right? Namely 1 is equal to minus C1 minus C1 minus 4 C2. Is it clear? So now I want to solve these two equations, right? Two equations and two unknowns. So we know many methods. By using any one of the methods, I hope very easily we can obtain C1 and C2. Is it clear? I hope you will get C1 is equal to 5 by 3 and C2 is equal to minus 2 by 3. Right? So we can substitute these values in this equation. I hope we can obtain a particular solution, namely x of t is equal to 5 by 3 into e to the power minus 1 into t minus 2 by 3 into e to the power minus 4t is the particular solution of the given differential equation. Right? So now you want to draw the curve, whether it is an underdamped motion or not, you want to verify. Is it clear? Right? So when we observe the curve, we will come to know whether it is an overdamped curve. Is it clear? Right? So how we are going to interpret? The problem can be interpreted as representing the overdamped motion of a mass on spring. The mass starts from a position 1 unit below the equilibrium position. Right? It starts from below the equilibrium position. Right? I want to repeat once again. The mass starts from a position 1 unit below the equilibrium position with a downward velocity of 1 feet per second. Is it clear? Right? The finally means as time increases, right, it reaches the equilibrium position. That is the meaning of the curve. Okay. Exactly in the similar way, now we are going to interpret what you mean by critically damped. Right? So again we want to calculate the value of lambda square minus omega square. Right? Suppose if it is equal to 0, the system is said to be critically damped because, right, any slight decrease, right, any slight decrease in the damping force would result the oscillatory motion. Right? The general solution is x of t is equal to C1 e to the power m1 t plus C2 into t e to the power m1 t. Friends, we know that if lambda square minus omega square is equal to 0, then we will get roots real and equal. Right? In that case, we can write down the general solution in this form, or we can write down the solution in this form. X of t is equal to e to the power lambda t C1 plus C2 t. Is it clear? Right? So here we can note that the motion is quite similar to the overdamped system. Is it clear? It also observed that mass can pass through the equilibrium position at most one time, or most of the time mass may crosses the equilibrium position in this case. right, either from the top or from the bottom, right. So, it means suppose if you take this is the equilibrium position, right. So, you may obtain a curve like this, or you may obtain a curve like this, or curve may be from the below, is it clear, or you may get curve like this. So, this type of curves we call it as an critically damped. Okay. We can solve one such type of example. It is given that solve the initial value problem, d square x upon dt square plus 8 into dx by dt plus 16x is equal to 0, right. They have given x of 0 is equal to 0, x of single prime of 0 is equal to minus 3, is it clear, right. Now, as usual it is an usual, in the usual form we can write down in symbolic form, again replace d by dt by capital D, capital D square x plus 8 into capital dx plus 16x is equal to 0, right. Again replace capital D by m, we can obtain the auxiliary equation, right. So, d square plus 8m plus 16 is equal to, so this can be written as m plus 4 whole square, or you may write in this form m plus 4 into m plus 4 is equal to 0, right. So, as I have mentioned, you will get first factor is equal to 0 or second factor may be equal to 0, is it clear. If first factor is equal to 0, then you will get m1 is equal to minus 4, m2 is also equal to minus 4. So, it means when we observe the roots, we will come to know that roots are equal, real and equal, right. So, the solution can be written in this form, x of t is equal to c1 e to the power minus 4t plus c2 into t into e to the power minus 4t, is it clear, right. So, now I want to use the given conditions. What are the given conditions? X of 0 is equal to 0, is it clear. I hope I can obtain the arbitrary constant c1, c1 becomes 0. I have to replace t by 0, so it becomes 1 and x of 0 is equal to 0. So, I hope we will get c1 is equal to 0. Now, I am going to differentiate this equation in the usual format, is it clear. As I have mentioned, it is of the type e raised to minus ax, right. I hope we will get x of single prime of t is equal to minus times of 4 into c1 e to the power minus 4t plus c2 into minus 4 times of t into, because I want to use u into v formula, is it clear, because t into e to the power minus 4t, right. So, using the product formula I can differentiate and I can obtain c2 into these two terms, is it clear, right. So, I can use the second condition, x of single prime of 0 is equal to minus 3, right. I am going to replace this by minus 3 and I will replace t by 0, simplify, I hope we will get c2 is equal to minus 3. It means I can obtain c1 and c2. So, now I will substitute c1 and c2 in this equation. Finally, what you will get, x of t is equal to minus times of 3t into e to the power minus t is the particular solution, right. So, when we draw the graph, I hope I may get a graph like this. So, finally, it reaches the equilibrium position, right. So, it will start from the above, then it will cross the equilibrium position, then finally, it reaches the equilibrium position, right. So, we call it as an critically damped, right. Friends, exactly in the similar way, now we can define one more form, namely under damped, right. So, when we call it as an under damped, now as usual we want to find out lambda square minus omega square value. Suppose if it is less than 0, is it clear? In this case, the system is said to be under damped because the damping coefficient is small compared to the sting constant, is it clear? Now, as I have mentioned, we want to find out the relationship between beta and k, is it clear? Here damping coefficient beta may be less than spring constant. In that case, we can obtain lambda square minus omega square less than 0, is it clear? It means we can obtain the complex roots, is it clear, right. So, how we are going to write down minus m1 is equal to minus times of lambda plus square root of omega square minus lambda square I. M2 is equal to minus times of lambda minus square root of omega square minus lambda square I. Is it clear? The general solution is x of t is equal to, right? So C1 into e to the power m1 plus m2t. Is it clear? Here roots are complex. We can write down in this form e to the power lambda into t plus C1 cos of square root of omega square minus lambda square into t plus C2 into sine of square root of omega square minus lambda square into t. Is it clear? The motion is described by x of t is equal to, right? So it can be, motion can be described by using this equation, right? So clearly it is an oscillatory, but because of the coefficient a to the power lambda t, right, the amplitude of the vibration tends to 0 as t tending to infinity. Is it clear? Right? So this factor or this term is present in this equation, right? That's why, so curve may tending to an equilibrium position as time increases. So that is the meaning, right? You can observe it may looks like this, finally maybe tends to 0. That's why it is called under damped, or sometimes we call this curve as an over damped, right? We can solve one such type of example, maybe in this form d square x upon dt square plus 2 times of dx by dt plus 10x is equal to 0, x of 0 is equal to minus 2, x of single prime of 0 is equal to 0, right? So in the usual form we can write down the auxiliary equation, right? First we want to write down in symbolic form, then replace capital D by m. I hope I can obtain m square plus 2m plus 10 is equal to 0. So therefore roots are complex. m1 is equal to minus 1 plus 3i, m2 is equal to minus 1 minus 3i. Is it clear? When you observe the roots, we will come to know that roots are complex. So therefore it can be written, or solution can be write down in the form of e to the power minus t. Why it is minus t? Because roots are complex, can be written down alpha plus I beta, alpha minus I beta. The value of alpha is minus 1. That's why according to the principle, superposition principle, we can write down e to the power minus 1 into t, or it can be written as minus times of t e to the power minus of t into C1 cos the value of beta is 3, cos beta t plus C2 into sine of beta t, right? So using the initial condition, they have given x of 0 is equal to minus 2, obtain minus 2 is equal to C1, right? So it means by substituting we can obtain the value of C1, right? Similarly, using the another condition, namely x of single prime of 0 is equal to 0, we can obtain one more constant, namely C2 is equal to minus 2 by 3. So we can substitute C1 into C2 in this equation, right? So finally we will get a particular solution e to the power minus t minus 2 times of cos 3t minus 2 by 3 sin 3t, and you can draw the graph of a solution curve. Is it clear? And you may get a curve like this. Is it clear? So initially it is a damping, right? As time increases, right, it will merge with the equilibrium position. That is the meaning of the curve. Okay, friends, so far we have discussed about spring mass system, have explained the meaning of damping, over damping, critically damping, right? So now we can consider a similar type of equations, right? So how a differential equation behaves in electrical sciences, right? So we shall discuss about that, right? So consider the single loop series circuit containing an inductor, a resistor and the capacitor, right, as shown in the following diagram. Is it clear? Right? So we can represent namely capital L, C, R. R means resistor, C means capacitor. Is it clear? Right? The current in a circuit after a switch is closed. So we can close the switch, right? Current will pass through the circuit, and it is denoted by I of t. Current is denoted by I of t, right. The charge on a capacitor at time t is denoted by Q of t. Is it clear, right? The letter L, C and R are known as inductance, capacitance and resistance respectively, and are generally constant. It means L may be a constant, R may be a constant, C may be a constant. That is the meaning of this diagram. I have given diagram as well as symbols, right. Exactly in the similar way, now according to Kirchhoffs second law, the impressed voltage E of t on the closed loop must be equal to the sum of the voltage drops in the loop. That's clear, right. So now what do you mean by inductor or inductance L, right? So we use the notation Henry or unit Henry. Voltage drop across is denoted by L into di by dt. That's clear. This is the circuit and this is the formula in case of inductor, right. Similarly, a resistor, resistance R is denoted by in terms of ohms. That's clear. Ohms voltage drop across I into R. So this is the symbol and this is the formula. That's clear. Exactly in the similar way, capacitor, capacitance C, right. How we are going to denote it by using the notation farad or F. Voltage drops across 1 by C into Q, right. This is the formula, this is the symbolic notation. This is clear. So now we want to add all the terms. Above figures shows the symbols and the formulas for the respective voltage drop across an inductor, right. A capacitor, a resistor, since a current I of t is related to charge Q of t on the capacitor by I is equal to dq by dt. That's clear. By adding 3 voltage drops, namely inductor, resistor, capacitor, how we are going to denote mathematically? L into di by dt is equal to capital L into d square q upon dt square. Similarly, IR is equal to R into dq by dt, and capacitor is denoted by 1 by C into Q, right. And equating the sum of the impressed voltage, we obtain a second order differential equation. Is it clear? So it means when we add these 3 terms, so we will get L into d square q upon dt square plus R into dq by dt plus 1 upon C into Q is equal to E of t, right. So mathematically it is a second order differential equation. How do we say that it is a second order differential equation? Because highest derivative is d square q upon dt square. That's why it is an second order first degree differential equation, right. And just now I have mentioned L is constant, R is constant, C is constant. Is it clear? That's why we can say that so this is an second order linear differential equation with constant coefficients, right. So friends, so far we are familiar with how we are going to solve a second order linear differential equation with constant coefficients. Exactly in the similar way we can find out the solution of this equation, right. And it is a non-homogeneous term, right. The entire equation we may call it as a non-homogeneous, right. So time being, if you want, you can replace E of t by 0, then it becomes an homogeneous equation. So you can solve homogeneous equation, then we will try to find out the solution of a non-homogeneous equation. Is it clear, right. So before that, the nomenclature used in the analysis of circuit is similar to that used in the to describe spring mass system. Is it clear? I have already solved a similar type of equation in case of a spring mass system, right. As I have mentioned, if you replace E of t by 0, the electrical vibrations of the circuit are said to be free, right. Since the auxiliary equation for L into d square q upon dt square plus R into dq by dt plus 1 upon C into Q is equal to E of t, right, is L into m square. It means as usual replace d by dt by capital D. Is it clear? D by dt by capital D, and finally replace capital D by m, right? So we can obtain this equation, L into m square plus R into m plus 1 upon C is equal to 0. Is it clear? Right? So there will be three forms, three forms of the solution. Just now I have mentioned, right? We want to find out the value of lambda square, omega square. Exactly in the similar way, now here also we will get three types of values, right? With R is not equal to 0, depending upon the value of the discriminant. In the previous case I said that lambda square minus omega square. Here I am saying that R square minus 4L by C. Depending upon the equation, discriminant may change. Is it clear? Exactly in the similar way, according to our equation, here I can obtain the value of R square minus 4L by C. The total value I may call it as the value of the discriminant, right? So it may be less than 0, may be equal to 0, may be greater than 0. According to that we can declare, right? So as I have mentioned in the following, right? So we say that the circuit is over damping, right? So when we say that over damping, if the value of R square minus 4L by C is greater than 0. Is it clear? Sometimes we can say that critically damped if R square minus 4L by C is equal to 0, and sometimes we can say that under damped if R square minus 4L by C is less than 0. Is it clear? We have to calculate the value of the discriminant. According to that you can declare exactly in the earlier way, right? So in each of these cases, the general solution of the given differential equation, right, depends upon the factor e to the power minus times of R into T divided by 2L. Is it clear? So this factor plays an important role, right? How we have discussed in the earlier cases, and the value of Q of T charges may tends to 0 as T tending to infinity, right? In case of under damped, right, Q of 0 is equal to Q naught, say some constant, right? The charge on the capacitor oscillates as it decays. Is it clear? So it means initially you may get a damping. It means spring, how spring moves from downward and upward direction, as I have explained in the earlier cases. No, exactly in the similar way, the charges may tends to an equilibrium position, right? Exactly in the similar way, the charge on capacitor oscillates and finally it decays. It means it tends to 0, right? In other words, the capacitor is charging and discharging as T tending to infinity. Is it clear? When E of T is equal to 0 and capital R may be equal to 0, the circuit is said to be under damped, right? And the electrical vibrations do not approach 0 as T increases without bound, right? The response of the circuit is simple harmonic. Simple harmonic means you may get a sinusoidal curve. Is it clear? That is the meaning, right? Okay, I am going to consider a similar type of equation, right? D square I upon dt square plus R by L into di by dt plus 1 divided by L into C into I is equal to 0. Is it clear? Right? So represents a current I. Is it clear? Flowing in an electrical circuit containing resistance R, inductance L and capacitance C connected in a series, right? If resistance is equal to 200 ohms and L is equal to 0.20 Henry and C or capacitance is equal to 20 into 10 to the power minus 6 farads, right? Solve the equation for I given the boundary conditions that when T is equal to 0, I is equal to 0 and di by dt is equal to 100. Is it clear? So we can write down same equation in this form, right? Given equation that is equal to, I have replaced d by dt by capital D, d square plus R by L into D 1 divided by L into C into I is equal to 0. In the earlier equations we have considered x is common, here I is common, you can take out. Is it clear? Right? And where capital D is d by dt. Is it clear? Right? So now you can write down the auxiliary equation. Is it clear? Auxiliary equation is simply replace capital D by m, right? So m square plus r by L into m plus 1 divided by L into C is equal to 0. Is it clear? I hope from the auxiliary equation we can find out the roots. Is it clear? Suppose if we calculate roots, so you can obtain roots in this form, right? So minus times of r by L into square root of r by L whole square minus 4 times of 1 divided by L into C whole divided by 2, right? So here r is equal to, they have given r is equal to 200, capital L they have given, C they have given, right? So now I want to substitute all the known values, right? And I have to simplify. It is a very simple case. I hope we can substitute and we can simplify, and finally I can obtain the value of m, right? I hope I will get minus 500. How many times? 2 times, because given equation is an second order differential equation. That's why, so you will get minus times of 500 2 times, right? So it means we will come to know that roots are real and equal, right? So in case of real and equal, how we are going to write down the solution? I is equal to a into t plus b into e to the power minus 500 t, right? So here a and b are arbitrary constants, and they have given the initial condition. So now I want to find out the value of a and b. How we are going to find out the value of a and b? In the usual form. So you can substitute t is equal to 0, I is equal to 0, right? So you can obtain b is equal to 0, and you can differentiate this equation with respect to t. You will get di by dt, because they have given one more condition. Now I want to use that condition, right? So t is equal to 0, di by dt is equal to 0, and I hope after simplification you will get a is equal to 100. Is it clear? Now I will replace b by 0, a by 100, and I can obtain I is equal to 100 into e to the power minus 500 t. Is it clear? Right? If you want, you can draw the curve of the same equation. You will get a similar type of curve, right? Sometimes we call it as an underdamped series circuit, right? So find the charge q of t. It is also a similar type of equation. They have given find the charge q of t on the capacitor, right, in an LRC series circuit when L is equal to 0.25 Henry, R is equal to 10 ohms, C is equal to 0.001 Farad. Is it clear? They are given E of t is equal to 0 volts, right, and Q of t is equal to Q naught coulombs, and I of 0 is equal to 0 amperes. Is it clear? Right. So now we can write down in the form of equation. How we are going to write down in the form of equation? L into d square q upon dt square plus r into dq by dt plus 1 upon c into q is equal to E of t, right. So they have given L 1 upon c is equal to 1000, right. So it can be written as 1 by 4 into q double prime plus 10 q single prime plus 1000 into q is equal to 0. Is it clear? Or the same equation can be written in this form: q double prime plus 40 into q single prime plus 4000 into q is equal to 0. It means multiply both sides by 4. I hope we can obtain this equation, right. Solving this homogeneous equation, it becomes an homogeneous equation. Right hand side becomes a 0. Is it clear? In the usual manner, and I hope we can find out the values, means roots. I hope we will get roots in this form. M1 is equal to minus 20 plus or minus 60i, right. So you can write down the solution. Is it clear? How we are going to write down the solution? Q of t is equal to e to the power minus 20t c1 cos 60t plus c2 sin 60t. Is it clear? If you apply the condition, I hope we will get c1 is equal to q naught and c2 is equal to q naught by 3. So you can substitute these values in the equation. Finally, I can obtain q of t is equal to q naught e to the power minus 20t into cos 60t plus 1 upon 3 into sin of 60t. Is it clear? So friends, when you draw the graph, I hope you may get a graph like this. Initially damping, finally it tends to an equilibrium position. Is it clear? Right? The motion described by the solution of the given equation is oscillatory, but because of the coefficient of exponential term, right? The amplitude of vibration tends to 0 as t tends to or x tends to infinity. Is it clear? That is the meaning, right? Okay, friends, so far we have discussed about a homogeneous equation. Is it clear? Right? So now we shall think about a non-homogeneous equation. Non-homogeneous equation means when the right hand side member is not equal to 0, how we are going to find out the solution of such type of equations. Is it clear? Right? The given equation may be in this form: a y double prime plus b into y single prime plus c into y is equal to f of x is called a non-homogeneous second order linear equation with constant coefficients, right? The non-zero right hand side of such an equation is often called a forcing function or the input or the driving function. It means this we call it as an forcing function. Is it clear? Or input function or driving function. Is it clear? Right? The fundamental fact about the linear equation is the general solution of a linear non-homogeneous equation, right, of this type is obtained by finding a particular solution of the non-homogeneous equation and adding it to the general solution of the associated homogeneous equation. It means so far we have discussed with homogeneous equation, and we know that how we are going to calculate a solution of a homogeneous equation, right? So for example, if you obtain roots, you may get real and equal roots. We will write down the complementary function, or we will write down the general solution x is equal to or y is equal to, right? Here if the if the right hand side term is not equal to 0 or non-zero, so in that case the complete solution of this type of equation can be written down in this form: y is equal to complementary function plus particular integral, right? So we want to calculate separately. First we want to calculate complementary function, then you can calculate a particular integral, and we are already familiar with how we are going to calculate a complementary function, right? Now we shall think about how do we calculate a particular integral. Is it clear? Right? So for homogeneous second order linear equation with constant coefficients, right, the proper form of superposition principle. Is it clear? How we have used superposition principle in case of homogeneous equation? Exactly in the similar way here, y1 is a solution of an equation like this. It means a into y double prime plus b into y single prime plus c into y is equal to f1x, a forcing function f1x, right? And y2 is a solution of another equation, a into y double prime plus b into y single prime plus c into y is equal to f2x. Is it clear? Then you can write on y is equal to c1 y1 plus c2 y2 is a solution of a into y double prime plus b into y single prime plus c into y is equal to c1 f1x plus c2 f2x, right, where c1 and c2 are the constants. Is it clear? Right? So now we can use this concept to write the general solution of the given equation. Is it clear? So friends, as I have mentioned, when the right hand side member is not equal to 0, so in that case the complete solution of the given equation is y is equal to complementary function plus particular integral, right? So now we are already familiar with complementary function. Now we shall think about how we are going to find out a particular integral, right? At the beginning of this session, I have mentioned right hand side member may be of the type e raised to ax. Is it clear? When the right hand side member of the e raised to x, how we are going to find out the particular integral. Is it clear? Right? Now as usual, given equation can be written down in case of a symbolic form, right? Then symbolic form is also denoted by f of d, right? F of d means a function of d. Is it clear? So this is the right hand side member 1 upon f of d e raised to x. Now I will replace d by a. Is it clear? right? A is what? Coefficient of x, right? I will rewrite it as 1 divided by f of a e to the power ax. Is it clear? Where f of a is not equal to 0, I have to verify whether a is f of a is equal to 0 or not. If it is not equal to 0, right? For some a is equal to 0, it means when f of a is equal to 0, for some d is equal to a, right? In that case, it means f of d is equal to 0 for some d is equal to a, then the above method fails. It is a very simple concept. First I won't write in case of e raised to x 1 upon f of d e raised to x, I have to replace d by a. I have to verify whether f of a is equal to 0 or not. Suppose if it is f of a is equal to 0, then this case fails. In such a situation, so we can use this formula, x into e raised to ax divided by some function of a which is not equal to 0 in case of f of d is equal to 0. Is it clear? Or otherwise, so we can use this formula, x square into e raised to x, right, 2 times of some other function. It means when a is double root of f of d is equal to 0, in that case we want to go for this formula. Is it clear? Right? I hope once again we shall discuss about particular integral in the next session. Thank you very much.